All right, recording and rolling. It's Tuesday, October 31st. Got a couple of starter questions for you guys about throwing a ball in the air. Uh, we'll work on textbook puzzles today. Those are due on Friday, so no time there. You guys remember tomorrow we got these fun 40-minute classes. Oh, where's my, oh, here it is. Okay, 40-minute classes. So tomorrow's schedule is going to look like this. Right, you go period one, period two, and then you go to your homeroom class, right, before you go to third. And you're having lunch with your fourth period class tomorrow. Do you guys check with your fourth period teachers? You guys know what lunch you're going to have tomorrow? Right, like I know my own lunch, C lunch. So, right, so that's tomorrow, 40-minute classes. And then Thursday, I think it's going to be a good day for this pulleys lab with chemical advantage pulleys. All right. So start a question here. You throw a ball straight upward at 10 meters per second. What's the maximum height? And then what if later on you triple that throwing speed to 30 meters per second? What's the maximum height? Hey, I think I could have asked you guys that question back in like September, and you guys could have answered that question using like kinematic formulas. Right, you guys remember? Oh, Three Amigos. You guys remember these guys? Right. So which one of these is probably best to answer the question, what's the maximum height based on throwing speed? First, second, or third? There might be more than one way to do it, right? But I'm looking at that third one because that third one has something to do with, okay, something to do with speeds and something to do with displacement. And if the question is what's the maximum height, that's a displacement question. Okay? So why do I like that more than the first two? The first two doesn't say anything about, well, right. Okay, because you could have maximum height, you could have throwing speed, right? But it'd be kind of difficult to figure out exactly what time that would correspond to, right? You would need to bring in the second one. And the second one, see what's special about maximum height? Guys, what do you know about the speed at the maximum height point? It'd be zero speed at maximum height, right? So that is actually one of your three kinematic values you could use to set up and solve this, right? So you could figure out the time, right? But then the second one by itself doesn't say anything about displacement, about maximum height. So you have to kick that back to the first one after you figure out the time and plug it that way. So you could use a combination of the first two, right? But I'm just going to go straight to the third one. You solve it that way. Let's try that. So let's get a picture going. Got a ball, got to throw it up at some initial speed. And then it's going to go to some maximum height. H max. Right? And what's special about that maximum height point, as you guys said, is that the speed right there, V final equals 0 meters per second, right to the right top. Right? So yeah, I could break out VF squared equals V naught squared plus 2AX. Right? So we're doing it the old way first. This is, goes back to some of the first stuff we did, kinematic motion. Right? And then later on, I'll show you guys, you do conservation of energy, you should end up with the same answer. Right? Right. So I'm gonna modify this. I'm gonna say this goes to 0 meters per second. Plug in there. Right? Now that corresponds to like a maximum height scenario. Right? So I'll leave throwing speed as just throwing speed. Okay. And then instead of plus 2AX, because that's really generic, I know the acceleration is acceleration due to gravity, talking about gravity field. I also know I'm throwing upwards, but the gravity's pulling downwards. So I need a negative sign somewhere. Right? And this X is displacement. But if I already determined 0 final speed, then we're talking about the maximum height. So I'm going to say minus 2G H max. Right? Maybe like that. Okay, so this could answer both those questions. You throw it up at 10 meters per second, and later on you throw it up at 30 meters per second. Okay? So I have it in terms of variables. Okay? So let's solve what is that H max. So let's go ahead and get this in terms of variables. You guys can solve in terms of variables, right? Right? So it's the same algebra processes. Right? So just before I plug in numbers, so I can add this term over. So I get 2G H max that we're solving for is equal to the throwing speed squared. Right? So isn't the maximum height going to be the throwing speed squared divided by 2 times the gravity field? Right? So now I have a general expression. I can figure out based on any throwing speed, how high does the ball go? For that matter, we could even change planets if we wanted to. So let's see what it is for 10 meters per second and Earth gravity. So H max is, because I'm going to plug in 10 meters per second. We're throwing straight upwards. Right? Square that. Divide by 2 times Earth gravity. Meters per second squared. Right? Is that 100 divided by 20? Is that like 5 meters? Okay, 5 meters. We got 5 meters. Okay. If you throw a ball straight upwards at 10 meters per second, it's going to go 5 meters high. For that matter, if you throw a ball straight up and you break out a meter stick and it goes 5 meters high, you can say, oh, I must have thrown it at 10 meters per second. Okay. What about the second question I asked? The second question I asked was, what if you triple that throwing speed to like 30 meters per second? How does that work out? H max is, right? So let's take this all the way to 30 meters per second. Let's square that, divide by 2g meters per second squared. Just like there. Okay. Let's do calculator. So it's 30 squared divided by 2g. Okay. I'm looking at like 45 meters. Right. Ooh, interesting. Guys, you triple the throwing speed. Did the height also triple? No, the height increased by a factor of what? 9 times. Ooh, right? You triple the throwing speed, the ball actually goes 9 times the height. Right. Oh, you know what that kind of sounds like? It kind of reminds me of, let's see if I can find this poster. Here it is, right? You guys remember a car braking to a stop? If you go like 3 times the initial speed of the car, you end up needing like 9 times the road to brake to stop. Huh. And then it comes out of conservation of energy. Huh. I wonder if there's a connection there. Let's go back and answer the ball throwing question, like maximum height. Let's use the new method, and the new method is conservation of energy. Okay? And say energy is conserved from here to here for the ball Earth system. So now let's do the ball Earth system. So we got a closed system. Right? Ball and Earth are pulling on each other, but all the forces are internalized. Okay? I can say the sum of energy at the bottom is equal to the sum of energy at the top. Okay? And what type of energy at the bottom? What type of energy right here? Okay, so just left your hand is moving really fast. It has a lot of kinetic energy. I'll call it all 1/2 mv squared. Right. Subscript now. We'll call it basically ground level. Right. So if the person has like some height above the ground, we won't care about that, right? So the point that the ball leaves the hand, we'll call that height 0. So there's no gravitational potential energy. Okay? But at the very top, ooh, right? Now there's no more kinetic at the top if you throw the ball straight up, has 0 speed for 1 instant. But there's a bunch of what kind of energy? Gravitational potential energy. And what's the expression for that? MGH, right? With that. Okay. Oh, I never gave you the mass of the ball. Is that okay? That I never gave you the mass of the ball? Because what happens right here? Cancels out. Right? Like the old way we saw it with kinematic motion. We back in kinematic days, we never had mass, right? Okay. But here there is mass, but it cancels out. Right? Right. Then say I want to solve for this h in terms of that throwing speed. I can just divide both sides by g, right? Divide the g down. I'm going to get h is throwing speed squared divided by 2g. Okay. Is that the same thing we got before? That is the same. Look at that, side by side. Here's the kinematic way of doing it. Here's the energy way of doing it. It comes out to the same thing, right? So it's the same solution, right? And then, well, if you plug in numbers, I mean, just work out like this anyway, right? Here's where I could point out too, like this relationship. So I like to ask proportional questions in this class, right? Like if you throw it up to some speed and it goes to some height, whatever, right? And then you go and you throw it 3 times the speed. According to this, guys, what's 3 squared? That's going to translate to 9 times the height, right? Which is exactly what these specific numbers say too. Because 5 times 9 would be 14. All right. So you guys got good warm up. Yes, sir. All right. Okay. Next thing. Let's look at these textbook puzzles. So I know yesterday we did these two. Well, I changed the numbers, but then I solved them for you guys. Right. I'll try maybe something a little different here. I don't know how this is going to work out, but let's try something here. What if I show you guys how to set these up? Okay, but I leave it kind of generic, and then yeah, we'll see how this plays out. Right. My plan is, I hope this actually works out, to give you guys time in Teams tomorrow, but I'll have slightly shortened classes tomorrow to work this out, right? But at least I can show you the setup and have you guys actually think about it. Maybe that's a better way to learn, right? May just like spit numbers at you. Right, we got 67 escalator. Sao Lan has mass 52 kilograms. She rides escalator at Ocean Park and Hong Kong. World's longest escalator with length of so many meters and average inclination of so many degrees. How much work does the escalator do lifting her up to the top? Right. So yeah, instead of solving this whole thing out for you, maybe I'll just draw a picture and write in some variables and show you guys maybe a framework to solve this. Right. We got this long escalator. World's longest escalator. Ocean Park. It's at an angle of, well, so many degrees, but maybe I'll just call it generic theta. Okay. Here's the rider, has some mass. Take her all the way to the top right here. Right. Right, they told you the length. Right. They told you what the angle was. I'll just say theta. Okay. Right. Now, there's a couple ways you could solve this, but they should lead to the same answer. One way to solve it, I think the way I might like to do it myself is I say, well, what if she had just ridden an elevator like straight up, just at this height change right here? Okay. Is that the same amount of work against gravity? Right? Just going up an elevator versus taking the escalator at some angle. Right? I think that's a it would give her the same potential energy at the end, wouldn't it? Right? So I think whatever potential energy she has, mgh, would answer the question. Okay? Guys, what is h in terms of L and theta? Be L times what? Sine or cosine? See, opposite is, it's not, yeah, opposite sine, right? Right, there you go. Right. So you could solve for that height that way, right? Alternatively, you guys know work is force times distance. And I made this whole point about being a dot product. You need to multiply by the cosine of the angle between them. So what's the deal with the sine? Because it looks like a sine's gonna come out of this, right? Because see, if you look at like say do free body diagrams, she's riding up. Yeah, let's do a peak vectors. How about that? Okay. She's got some weight, mg. There's a normal force which is going to be a little bit less than that because it's mg cosine theta. Mg cosine theta, right? And then, well, I guess there better be some maybe like applied force. If they're just pulling up at a constant speed, then I'll call it like F applied. Right, so like motor running right there, right? Okay. And the angle between the weight and the distance moved, that weight and the length, right, is actually, let's say, okay, would be this full angle right here, right? If that's, yeah, I think over there right here. Okay, yeah. So if I do F dot D, here's like your distance D. Okay. The force you need to apply, right, isn't that going to be equivalent to mg sine theta? Right, like this right here would be equivalent to that. Right, those two would be equivalent. Right, and this one is equal to mg sine theta. Right, so when I say that the dot product is defined as F times D times cosine of the angle between them, right, careful that the angle you were given does represent the angle between them, which in this case it doesn't, right? So sometimes this turns out with a sine instead of a cosine, right? Like in this case. Okay. All right, let you guys think a bit more deeply on that. Okay. So that's the setup. Kind of start to solve it. Okay, number 78. Graph shown in this figure shows force versus displacement Right. Yeah. Whenever you get to the energy section in a physics textbook, you'll see plenty of these graphs: force versus displacement. Right. My AP kids, I tell them whenever they see a force versus displacement graph to start thinking in energy terms. Right now, why would that be? Well, I know that force times distance is work. Okay. Let me find my graph poster. I know I've got a graph poster somewhere in here. No, it's not that one. Here it is. Here it is. Okay. Well, if work is force times distance, okay, then if you have a graph that has force on one axis and distance on the other axis, right? Force times distance, that sure does sound like a lot like base times height, right? So the area under a curve could represent the energy transfer. So there's your work, right? So if it's a constant force, which is how things usually play out, but you don't have to necessarily, right? Then it would be a rectangle, right? It could be the work done, like the energy transfer, right? Now this graph, okay, maybe not exactly a nice rectangle, but it's the same principle. Like the area under that curve would represent the energy transfer or the work done. Let's see if that's what the question is. It shows the force of displacement for an object being pulled. Right? So like pulling on an object. Right? It's like a variable force. Calculate the work done. To pull the object 7 meters. Ooh. So do you guys think it's the area underneath that curve? Right? And if you split this up, do you guys see a tiny triangle right there? I see a tiny triangle. And I see a nice looking trapezoid here, which is really just a skinny triangle sitting on top of a rectangle. Right? So if I start to hash these in, so I got this triangle right here. I got this rectangle right here. I got the skinny triangle sitting on top of that rectangle. And it says to 7 meters. Now here's the other tricky part, is 7 meters only goes up to right there. So you have to add a rectangle, but only up to like this line. Right? So you don't even use exactly the entire graph, right? You use a little bit less than that, only up to the 7 meter, right? You guys do that? Can you guys add together those 4 different areas? Right? A couple triangles, a couple rectangles. That's the question. Calculate the power that would be done if this was all done in 2 seconds. Okay. That time, 2 seconds, shows up nowhere on the graph, so they would have to give that to you, right? I don't see anything about time or time axis, right? So they told you that separately. But you guys know that power, this is what, number 78, let's zoom out here. Okay. Power is a rate of work or rate of energy transfer. Is that like work per time? Okay, so you could do however much work and then divide by the time. You could figure out that way. Right, you guys can do that? All right, number 81. A pulley system lifts 1345 Newton weight, distance of that many meters. Okay. Oh, notice they gave you the weight in newtons, right? If that's like 1300 newtons, what approximately is the mass of the object being pulled up? What's the mass in kilograms? I think 130 something, right? 134 something, right? About, right? Because it's about 130 something kilogram mass times gravity gives you 13 something Newton weight, or so 1300 Newton weight. Right? Distance of 70 meters. Paul pulls a rope a distance of, ooh, it looks like about 4 times that distance, doesn't it? Right? Exerting a force of so many newtons, right? We're talking about a pulley system here. Okay, it's this pulley system, right? We're getting like a mechanical advantage, right? So what is the mechanical advantage? How efficient is the system? Right? What's the right, ideal versus actual mechanical advantage? Okay. This looks like the lab I'm going to have you guys do on Thursday. So let's break out the lab posters for mechanical advantage. Okay. So here's a general pulley system. Now this one's showing 3-to-1 mechanical advantage, which is not exactly what's what the book is asking, but same principle here, right? So the principle that makes a pulley system work is that the work input is equal to the work output. So however many joules of energy you put into the system, like pulling on the spring scale on the left side, is equal to the number of joules of energy that go into lifting the object, gives it some potential energy, right? Right. So you can't amplify the amount of work or the amount of energy from the pulley system. It'd be nice if you could. If you could amplify the amount of energy, you could have like one lump of coal and it could run the entire world's energy supply forever. Right? But it doesn't work out that way. You have to keep mining new coal and blah, blah, blah. Right? So we're going to do force times distance equals force times distance. Right? So this tiny input force times a huge distance we're pulling lots and lots and lots of rope. Right? is going to lift a very heavy object, right? That's a huge output force, but it only lifts it a little bit at a time. So we go, this goes like, right? We're able to lift something that maybe otherwise we couldn't, right? Because we've like amplified our strength, right? Now, how much do you amplify your strength? Well, that's a mechanical advantage. There's actually two different perspectives on mechanical advantage. There's ideal versus actual, right? So I'll call it IMA, AMA, right? Ideal mechanical advantage, actual mechanical advantage. The ideal comes from the geometry of the system. You say, well, if there's no frictional loss, then you get like what's the maximum you could possibly get out of this, right? Do you guys see how there's like two fixed pulleys? Like these pulleys are not moving; they're just like spinning in place, right? But this pulley is a movable pulley. Can you guys imagine animation? This will like slide up and down, right? Or I've got one in class. So, sorry if you watch this video at home, you just have to imagine. But if you're in class, right? You guys see as I pull this, right? These two pulleys are fixed; they're not moving. But this one, ooh, that's a movable pulley. See how it's moving up and down with the weight? Is that right? Now my pulley system in class is like a 5-to-1 mechanical advantage. So like this string like loops around one more time because like 5 strings. But my cartoon version here, I've got like 3-to-1. Okay, so it's like the weight split 3 different ways. Suppose this object here weighs, I'm just gonna make a number, like 300 newtons. 300 newtons. Okay. Oh, guys, what is the tension in each one of these strings? What's 300 divided by 3? It's only 100 newtons, right? Okay, so 100 newtons transfers 100 newtons, 100 newtons, 100 newtons. Okay, and then by the time you get to the spring scale, I only have to pull with 100 newtons, right? So it's like I feel like 3 times as strong, right? The catch is you have to pull like 3 times the length of the rope. So if I pull 3 meters, right, then that also gets divvied 3 ways. So it only pulls up the object 1 meter, right? So 300 newtons going up 1 meter, that's like 300 joules that I lifted, right? So how much work do I have to input? Well, if I'm only pulling with 100 newtons, but I pull 3 meters, that's also 300 joules. 300 joules in equals 300 joules out, right? So energy is conserved, right? Now that's ideal, right? Now, in reality, maybe there's a little bit of frictional loss. Maybe these pulleys aren't exactly ideal. Maybe these strings aren't exactly vertical also, right? Like if they're off at some angles and that angle gets more and more horizontal, I bet that weight doesn't exactly split 3 ways, right? So like 100, this 300 newtons down might not be 100. It might be like I don't know, 105, 105, 105 or something like that. So maybe you don't get this exact ideal, right? It's going to be a little bit lossy, right? So what's the actual mechanical advantage? The actual mechanical advantage is like the ratio of these forces, right? So the forces being lifted compared to your input force, right? Now that can go up to, in this case, 3-to-1, but maybe it'll be a little bit less than that. Maybe it's like, I don't know, 2.751 or something like that. You guys get that idea? Okay. So on Thursday, when I have you guys do this lab, I'll have you guys rig up a few different pulley systems. Here could be 1-to-1 mechanical advantage where you're not really getting an advantage other than maybe like rerouting the direction. So you can pull down and pulls up, right? But you're not really amplifying your strength. You can do 2-to-1. Ooh, do you guys see 2 strings up versus 1 weight down? So if this thing weighs 300 newtons, how many newtons of pulling force do you think you need? What's 300 divided by 2? It's like 150, right? Should be 150. If it is 150 newtons, then the ideal and the actual mechanical advantage would match, right? But realistically, it's probably a little bit more than 150 newtons. Maybe it's like 180 newtons. So there would be a little bit of a mismatch between the ideal and the actual, right? Oh, here's the 3-to-1. There's a whole full-size poster for that, right? And then you could even do something like a 4-to-1. I do have some like double pulleys. Oh, here's like a single pulley. But I have some that are like 2 pulleys side by side. So these could be like kind of on top of each other, sort of, because they move independently of each other, right? But I see 1, 2, 3, 4 strings going up for that 1 weight down. 3 and 4-to-1, something like that, right? And then one I got in class right here is like a 5-to-1 mechanical advantage. So here's things you could measure on your lab on Thursday. Okay, what's the input force? So how much are you pulling? Right? What's the input distance? So like how far did you pull? Do you guys think you could put a meter stick right up next to this right? Like a meter stick right here, or a ruler? Probably a ruler would be a good scale, right? Okay. How far did you pull? Right? Then the output. Right? So there's gonna be like some lab weight here. Right? How many newtons is that lab weight? How much does it weigh? And then how far does it move up? Probably not very much. And you're only pulling up a little bit at a time. Right? The greater the mechanical advantage, the slower it moves up. Right? Ideal mechanical advantage means you take the ratios of the distances. Right? So that's based on geometry. Actual mechanical advantage you're going to take the ratios of the forces, right? Like how much did you actually amplify your strength by, okay? And hopefully they'll be pretty close to each other. Like if this one's 2 to 1, maybe this is like 1.8 to 1 or something, okay? All right. You guys get that? All right, so take one more look at number 81, right? So they told you the weight of the object and the exerted force. So if you divide those two, you should get the actual mechanical advantage. They told you the two distances. So if you divide those two out, you should get the ideal mechanical advantage. Right? And then, oh, finally, what's the efficiency of the system? So the whole premise of this working is that work input equals work output, right? And then I could set up this and then solve that, right? But if this is true, like if you have 100% efficiency, then you'll get the same ratios, like 3 to 1 here and also 3 to 1 here, right? But you probably get, like realistically, again, there might be a little bit of frictional loss, or maybe the streaks aren't exactly vertical or for whatever reason. Right? So there's probably realistically going to be a little bit of a mismatch. So the output work should be ideal, or I should say actually a little bit less than the input work is what you'll actually see. Okay. So there's two ways you can get efficiency. Efficiency. I'll call it Greek letter eta. Here, this is Greek letter eta. Right. A lot of times stands for efficiency. It's one way to do it. Right. One way you can do it is you can say, what is the work out compared to the work in? Right. Like if you put in 100 joules of work, but only 90 joules goes into lifting it, and the other 10 joules like going to like frictional losses or something. Okay, right. Something like that. Okay, so that would be the same thing as force out, distance out over force in, distance in. Right. Now the distances should work out like ideally like whatever ratio, like 2 to 1, 3 to 1, 4 to 1. Okay. But those forces, ooh, you might actually have to apply a little bit more input force than ideally you would have imagined, right? Okay. So that could be efficiency. Okay. Another way you can get efficiency is you could do what is the actual mechanical advantage compared to the ideal mechanical advantage, right? Which would be, what's that? F out over F in, all divided by distance in over distance out. I think these two have got to work out to be the same thing. Let me see if that's true. F out's right there. F in is in denominator. That works right there. Distance in is right here. Yeah, these are the same thing. Okay. So two little bit different approaches, a little bit different perspectives, but those do work out to be the same thing. Okay. There's two different ways you can calculate efficiency. Right. You guys can calculate efficiency? Okay. All right. All right, you guys good so far? You guys good on chapter 10? Chapter 10? There's 5 circled questions on chapter 10. I'll switch over and look at chapter 11. Now, chapter 11 is your conservation of energy, which is actually how I kickstarted this whole section. I said, well, all energy is conserved. You can't create or destroy energy. Therefore, you have this framework and you can solve lots of things, right? Energy takes different forms. Okay, kicks back to chapter 10. And so number 57 is the first one I circled. See what this says. Yeah, Tony has a mass of 45 kilograms and moving with the speed of 10 meters per second. Okay. Find what is his kinetic energy. Ooh, can you guys do 1/2 mv squared? Get his kinetic energy, right? His speed changes to only 5 meters per second. Oh, he slowed down, right? Now what is his kinetic energy? Right. Okay, so you just run 1/2 mv squared again, right? Right. We got to ask you guys. Oh, actually, I was going to ask you guys this question C, but that was the book's question. What's the ratio in kinetic energies? First of all, let's go ahead and answer that right here. Guys, if you have half the speed, what's the ratio of your kinetic energy compared, like new compared to old? Do you have half the kinetic energy? Or do you have a different ratio? If you have half your speed, what happens? Let's write this out. So 57. I know kinetic energy is 1/2 mv squared. Sometimes I do KE, sometimes I just do capital K. Right? I've been trying to switch to capital K. Right? Right, so 1/2 mv squared. Right? So let's say originally Okay, originally he had like 1/2 mv squared, just some values, right? And let's say the new kinetic energy is like 1/2 is the same, mass is the same, but now he's going to have half of his original speed squared, something like that, right? It's half the kinetic energy. Guys, what's 1/2 squared? It's like a quarter. I bet he's only going to have a quarter of the kinetic energy that he started with. Right? Same idea with the, just like my car braking to a stop. Right? This is a classic question I keep asking you guys over and over. It's like, if you change your speed, how's that change your braking distance? Right? So if you have twice the speed, don't you need 4 times the braking distance? Because you'd have 4 times the kinetic energy. So if you just reverse that and say, well, if I have half the speed, you only need a quarter of the braking distance. Right? Goes hand in hand. Right? So same thing here. If you divide these two, and then get set 1/2 squared is 1/4, v0 squared over v0 squared. Yeah, so the ratio of kinetic energies is going to be a quarter. Half the speed, you have a quarter of the kinetic energy. Number 60, car brakes. Oh, car brakes to a stop. Right. Just showing you guys that poster. They gave you how many newtons of weight the car is. I might really care about what is the mass of the car. Guys, 14,000 newtons. How many kilograms of mass is that? Is that 1,400 kilograms of mass? About? You just divide by 10, right? So 14,000 newtons, that's like 1,400 kilograms of mass, right? Just divide by 10, right? Moving at 25 meters per second. Okay, so if I take the mass, like 1,470 kilograms of mass, get 1/2 mv squared, that could give me the kinetic energy. The brakes are applied, suddenly the car brakes to a stop. Okay. Oh wow, look at that super realistic car. Look at that, right? Griffin turbo cars. Right? The average braking force is that many newtons. How far will the car slide once the brakes are applied? Right. So it looks like they're just the numbers they've given you is a little bit different than maybe. Actually, we could kind of use this, couldn't we? Right? Because we could use this framework. Because right? They didn't exactly give you the mass of the car, but you could figure it out pretty quickly. Just divide the weight by 10. Right? They did give you initial speed, so bam, you got that. Bam, you got that. Right? They told you the braking force, like the friction force. So bam, you got that. Can you guys plug everything in and solve for that braking distance? Can you guys do that? Right? Because do that, you can figure out the mass pretty quickly. Bam, you're given that. Bam, you're given that, and solve for that. Can you guys do that? Right, do that. Right. Right now, how I have it on this poster is I went a layer deeper and said something about coefficient of friction. So, just for fun, even though your book didn't ask you, let's solve what is the coefficient of friction for this particular scenario. You guys remember how to get coefficient of friction? It's like the friction force compared to the normal force. You guys remember that? Right? No, if this car's on a level road, isn't the normal force just equivalent to the weight? Well, since we've been through rotation, you guys remember there's like a 0.3% difference between those two, but I'll just say they're about the same, right? So let's take friction force they gave you as 7,100 newtons. I'll just go ahead and use their book number because I'm curious to see what is the coefficient of friction. And they told you the weight of the car was 14,000 Sohm newtons, right? Okay, so that would also represent the normal force. All right, let's do. What is 7100 over 14,700? Okay, so the coefficient of friction is 0.48. Yeah, okay. So that's really close to 1/2, right? That would correspond to a case of maybe it's been a rainy day, right? So you've got kind of a wet road, right? You brake into a stop. Right? If it was a dry road, it would be approximately double of that. You have new tires on the car. All right, so you guys good with the car braking to a stop? All right. And what I mostly care about car braking to stop is that interesting proportionality between initial speed and braking distance, just like a squared relationship. Right, number 61, so many kilograms cart is moving with a velocity of so many meters per second down a level hallway. Okay, level hallway. Now I know that there's no height changes. So I know there's going to be nothing to do with like gravitational potential energy. Don't have to worry about that. Okay. A constant force of so many newtons act on the cart, and its velocity becomes Ooh, slower. Ooh, slows down. This is like a stopping force, right? What is the change in kinetic energy? How much work was done? And how far did the cart move? So it's kind of interesting. Fine, where's my poster version of this? Right. This kind of reminds me of, I don't think it, I think my poster is a little bit more complicated than the question, right? Maybe something like this. I think we can ignore most of these forces, right? The fact that the car is slowing down, it could possibly be a friction force, or we could treat it that way. I think it'll give us the answer, right? So I'm really focused on like this type force, right? The cart's moving, say, to the right, and the friction force acting to the left. I think the friction force is doing negative work on the cart. That's not how it's going to be. So how do we do this? Right, 61. Question A. What is the change in kinetic energy? That's what delta K is, right? Change in kinetic energy. Right. One way you could do change in kinetic energy is you could do 1/2 mv final squared minus 1/2 mv initial squared. And I think you have all the numbers because you have the mass of the cart, goes right there. They told you the final speed, and they told you the initial speed. Yeah, you have all the numbers here. Just pop everything in. Just get it that way. Okay. Change in kinetic energy. Okay. Question B. How much work was done on the cart? Well, that would be the change in kinetic energy. That's something called the work energy theorem, right? So whatever work you do on something is a transfer of energy, right? In this case, it's all going to go into the kinetic energy because the cart's not going up any hills, right? There's no elevation changes, right? So all the change in energy goes into its motion, right? So the answer to question A and the answer to question B is the same thing. The exact same answer. It's going to be some negative number of joules. You're going to get a negative number, right? This cart's on it. Right. Question C. How far did the cart move while the force acted? Well, you guys know something else about work, and that's force times distance. It's the dot product of force and distance. Right? So if you know the work, which is the answer to both A and B, it's some negative number of joules, and you want to know the distance, okay, there's one other thing you have to know. You have to know what force was applied. Did they tell you that? They had to have told you that. Oh, yeah, they did tell you that. Okay, a constant force of 10 newtons. Okay, so yeah, you have that too. Okay, so now you can solve that. Okay, you guys can figure out number 61? Okay, so here, while you guys are putting that in your notes, run through that one more time. Okay, so your textbook asks you 3 different questions, and they sort of like lead into each other. So you solve one, it's like a setup for the next one, and so on. Right? First question said, what's the change in kinetic energy? Now, kinetic energy is 1/2 mv squared. They told you the mass of the cart in 2 different speeds. So you can just very simply do difference in kinetic energy. That answers that question. The second question said is, well, how much work was done on the cart? But that's the same question as the first question, right? Because the change in kinetic energy is the work done on the cart, right? Or the work done on the cart all transfers into the change in kinetic energy, right? Also, especially since there's no height change, right? You don't have to worry about potential energy, right? It's called work energy theorem. Okay? The third question is that, well, how far was the cart pushed for this whole scenario to play out? Okay? There's your force times distance. Right? And they told you the friction force. Go ahead and make this number negative because you got negative, so the distance will be forward. The cart's still moving forward. Okay? So yeah, negative equals negative times the positive. Okay. Right, you guys can solve that? Right, number 81. Hakeem throws a 10-gram ball. Come on. Okay, here. 10-gram ball straight down from a height of 2 meters. The ball strikes the ground with a speed of so many meters per second. What's the initial speed of the ball? Ooh. Right. So this sounds like an extended Galileo question. Right. So instead of just dropping the ball, now he's throwing it. Let's set up a conservation of energy for number 81. Throws the ball straight down. Right. They said 10 grams. Even before we start writing stuff down and plugging and chugging, do you guys intuitively feel that maybe that mass is probably going to cancel out? Right? Because this feels very kinematic, right? Just like a transfer of like potential kinetic energy. And I remember back in kinematic days, we never even cared about what mass of the object was, right? We said, oh, it's canceled out, right? Right. Now, if the mass did not cancel out, suppose there was like a spring involved or something where the mass did not cancel out, what would you have to do with 10 grams before you could do any calculations? You have to convert it to what first? Kilograms, right? Kilograms, right? Right. But I think we can bypass that anyway because I think it's going to cancel out. Let's do sum of energy initial equals sum of energy final. Right. So maybe here's a picture. Right. Take a ball. We're going to check it straight down. It's initial speed, and then it's going to be hitting the ground at an even faster speed. Okay. Get some straight marks here. Okay. Right. So for what kind of energy at the point that you threw it? Does it have gravitational potential because of this height? That's mgh. Plus it also has 1/2 mv squared from the throwing. So throw a little subscript naught on that v, right? Throw speed. Then when it's about to hit the ground, it's pretty well lost all of its height. But it has kinetic energy. In fact, it has all kinetic energy, right? When it's about to hit the ground, right? So isn't that like 1/2 mv final squared? Right, something like that. Right. There's your setup. Right. Oh, here's your 10 grams, cancels out. This way, right? What was the question again? What did they give you? Oh, they said what was the initial speed of the ball? Okay, so they're actually asking for the initial speed, the throwing speed. They told you the height, 2 meters. Bing, you have that. Pick your favorite number for gravity, either 9.8 or 10 meters per second squared. That Hawking's probably on Earth. Bing. And they told you the crash speed, how fast it strikes the floor. Bing. So you guys see how you have all the numbers except for the throwing speed? Okay. Okay. While you guys are writing that down, I did through my posters because this kind of reminds me of, let's see, if I can find it. Got so many posters anymore now. I think that's a good thing. Okay, here's one I'm kind of thinking of. This is not exactly the same scenario, but it does have some things in common. Okay, where's Galileo and his tower? Let's see if I can find Galileo and his, well. Oh, here's Galileo and his tower. Right. Right. So Galileo and his tower. Right. Now, if he drops the ball, here I'm showing if he drops the ball. You guys remember how the speed, the speed was always square root 2gh? That's if he drops the ball, right? Which is not what you're being asked in this question. What is this, number 81? Right. You're saying he throws the ball. Because if he throws the ball, how does this finish out? Should I do? I think I gave you guys this multiple choice question the other day. Let me rewrite this multiple choice question. If you throw the ball, is v final equal to, I'll give you guys option A or option B, and you guys tell me which one is correct. I'm about to write 2 expressions. One is correct and one is incorrect. Which one's which? Do you take square root 2gh and very simply add on the throwing speed? Or do you have to take a giant square root of the throwing speed squared plus 2gh? Right? Now, you could confirm by solving that conservation of energy that I just set up with you guys right here. You could figure out which one of those it is, right? But how does this play out? See, show hands, show hands. How many guys think the correct version is option A? Who thinks that? Nobody says that. How many guys says option B? Option B. That's everybody, right? Everybody says option B, right? So if you set up this conservation of energy right here and solve for this B final, it always ends up being like option B. Right? Now, why did I pull out this pendulum? Because what does that have to do with things? Right? Because this is effectively works out the same way, right? Where the speed at the bottom is equal to, oh, look at that. It's the kickoff speed squared, suppose you like push off, right, from the beginning, right? Okay, plus 2g, and then all this stuff is like h, right? The height change ends up working with this, with the geometry, right? Yeah, look, so this is actually like a pretty similar scenario. Right, and 84. Suppose a chimpanzee swings through the jungle on vines. Oh, swinging through the jungle. Hey, already I'm starting to think about this right here. Right, already think something about pendulum, maybe. Right? It swings on a tree. We've got a 13-meter long vine. Starts at an angle of 45 degrees, maybe from the vertical, but I guess either way, right? Oh, because 45 degrees. What is the chimp's velocity when it reaches the ground? Hey, I think the answer is right here. Yeah, so this goes through a lot of fun geometry, but it's solved on this poster. I think this poster is hanging somewhere in front of me, right? So one of these. So you guys have the answer kind of in front of you. Right? This is a good thing to be able to do, right? There's a little bit of complexity. You have to step through some geometry. So let me slow walk you guys through these steps. Okay? So if you want to figure out what's the speed at the bottom, you set up conservation of energy. You can say it's all potential at the top, mgh, and all kinetic at the bottom, 1/2 mv squared. Okay? They didn't say anything about the chimp pushing off, did they? Well, we're going to assume he starts from rest, right? So if he starts from rest, right? It says if he pushes off, you add this gray text, right? But if he starts from rest, you just ignore it, right? Then a lot of the fun of solving this pendulum is to go through the geometry to figure out what is the height change between these two dashed lines. So I'll walk through this again. I think you did the other, it's worth saying again, right? So the way you do that is you say, well, I see a nice right triangle here, and here's the starting angle from the vertical. So they called it 45 degrees. So you guys got an angle, right? And this leg of this triangle is L cosine theta. So that's L cosine theta, right? Right. Which means that the height gap is the difference between the full length of the pendulum and L cosine theta. Oh, that's this right here. L minus L cosine theta. If you like, you can factor the L out. Right, and then that would make it look like that. Right, so you guys get that too. All right. Oh, all right, just in time. We got 1 minute till the bell. You guys felt pretty good about those? Right. So, yeah. I think I can stick to my plan. I think tomorrow's going to be, I'll have you guys work in teams and solve these. And I don't know, I might have a couple of activities lined up, right? And then, there's lots of other questions too. Just have any questions about this, right? Also, I did finish writing your guys' quiz, so I think I'll get you guys your next quiz tomorrow and give you guys a few days to do that. Right. So next week we'll start momentum and collisions, which is all those posters over there with the blue banners. Then I'll give you guys another traditional take-home quiz. Okay. Then near the end of November, beginning of December, summer timeframe, I'll give you guys an in-class quiz. With it'll be on both energy, which we're doing right now, and also momentum, which we're going to start on next week. Okay, so that'll be an in-class quiz around end of November, beginning of December timeframe. All right, that's a wrap on today.